Welcome in this session. This session, we are going to prove some wave equations for some specific functions. So problems. So remember, the wave equation is an equation given by a squared f xx equals to f tt. That's to say that a squared partial squared f partial x squared is the same as partial squared f partial t squared. So we are trying to prove equations, to prove this equation, whereby the function f is in terms of x and t. So the first problem, so show that the function f of x comma t given by x plus at cubed satisfies the wave equation. So solution for this, we show that partial squared f partial t squared is the same as a squared partial squared f partial x squared. This is the wave equation. So partial f partial t, so use chain rule here. So fixing this to be u, so we have 3 and then x plus at, and then the power reduces by 1, so you have 2. You multiply by, when you differentiate inside with respect to t, you get a. So that partial f partial t, you have 3a x minus a t squared. And then partial squared f partial t squared means that we are differentiating this one again with respect to t. So this differentiate, fix this one to be u. So remember this plus sign. Fix this one to be u. So drop this power. We'll have 6a x plus at. Now you subtract 1 from the power, just have 1. And then differentiating inside with respect to t, we have, with respect to t, we have a. So this will be 6 a squared into x plus at. Now let's go to the function and differentiate it with respect to x. So we'll have partial f partial x equals to, do the same thing. Fix everything here to be u. So you drop, we'll have 3 into x plus at. Now power reduces by 1. And when you differentiate inside with respect to x, you just get 1. So this will give us 3 into x plus at squared. And then partial derivative of f squared with respect to x will be, differentiate this one again with respect to x. So if you fix this to be u, so dropping the 2 will have 6 x plus at. Power reduces by 1. And then when you differentiate inside, you get 1. So this will be 6 into x plus a t. Now, a squared, this implies that a squared partial squared f partial x squared will be given by a squared if you multiply by what we have gotten here, 6 into x plus at. And this is the same as 6 a squared into x plus at. So if we had called this one equation 1 and we call this one equation 2, clearly you see that 1 and 2 are the same. So equation 1 equals to equation 2 equals to 6 a squared x plus at. That is to say that partial squared f partial t squared is the same as a squared partial squared f partial x squared. So therefore, that function satisfies the wave equation. Example 2, if we have f, let's this is a bit not f. So they have u x comma t given by sine x plus at. So for this one, we show that solution. We show that partial squared u partial t squared equals to a squared partial squared u partial x squared. So that let's start partial u partial t is given by now. Differentiating this one with respect to t, fix this to be u, so that now use chain rule. Differentiating this with respect to t, we get a. When you differentiate a sine function, you get a cos function. And then this implies partial squared u partial t squared. Now you differentiate this function. You know, when you differentiate a cosine function, you get a negative sine function. So we'll have a negative sine a. And then differentiating this part with respect to t, we get a. So a times a will be a squared. Then sine of x plus at. So call this one equation 1. Partial u partial t partial x will be differentiating a sine function, you get cos function. When you differentiate inside here with respect to x, we get 1. So 1 times this gives us just sine cos of cosine of x plus at. Now this implies that partial squared u partial x squared, differentiate this one again with respect to x. So when you differentiate a cos function, we have a negative sine function. Inside here, when you differentiate with respect to x, you get 1. So 1 times that one, you get sine x plus at, which means that if I say a squared partial squared u partial x squared, then I'll have a squared into this one is minus sine of x plus at, which simplifies to minus a squared sine of x plus 80. Call this one equation 2. You see, equation 2 and equation 1 have the same values. You see this and these are the same. So clearly, equation 2 equals to equation 1 equals to minus a squared sine x plus 80, i.e. partial squared u partial t squared equals to a squared partial squared u partial x squared. So that function satisfies the wave equation. Another example, number 3, if we have a function phi of x comma t given by e raised power x minus at. So we also need to show that phi satisfies the wave equation. So solution, we show that partial squared phi partial t squared equals to a squared partial squared phi partial x squared. So this is the wave equation. So partial phi partial t, we use chain rule. So fix the power to be u. So when you differentiate that u with respect to t, you get negative a. So we'll have negative a and then e raised power x minus at, which implies that partial squared phi partial t squared. Now differentiate this one with respect to u. Also use chain rule and fix this one to be u. Differentiate with respect to time again. This one here. When you differentiate the power with respect to t, you get minus a. So that minus a pre-multiplies this function. So we'll get positive a squared. And then e raised power x minus at. So call this one equation 1. Next one, partial phi partial x. So differentiate the power with respect to x, you get 1. So 1 times the function, you get here the same function. So you have e raised power x minus at, which means that partial squared phi partial x squared, differentiate this one with respect to x, you get 1. 1 multiplies the function itself, we have the same thing, x minus at. So call this one say equation 2. So if you say a squared partial squared phi partial x squared, we'll have a squared into this one, we have the answer as e raised power x minus at, which is a squared e raised power x minus at. Call this one equation 3. Do you see that equation 1 and 3 are the same equations? Or this and these are the same. So clearly, equation 1 equals to equation 3 equals to a squared e raised power x minus at. Therefore, the function satisfies the wave equation given by partial squared phi partial t squared equals to a squared partial squared phi partial x squared. And lastly, if we have a function v given by x comma t of the form sine x plus 2t, so show that satisfies the wave equation partial squared v partial t squared equals to 4 partial squared v partial x squared. So that's the problem. So as usual, start by getting the first partial derivatives. So solution or proof. Partial v, partial t, and differentiate this function. So these are sine function. When you differentiate it, you get a cos function. Now, when you differentiate this part with respect to t, you get 2. So we'll have 2 cos of x plus 2t, which means that partial squared v partial t squared. So differentiate this one again. When you differentiate a cos function, you get a negative sine function. So we'll have a negative sign. And when you differentiate this part with respect to t, you get 2. So that 2 by this 2 gives us 4. X plus 2t. All this one equation 1. And then let's now partially differentiate that function with respect to x. So when you differentiate a cos function, you get a sine function, you get a cos function. Differentiating this part with respect to x, we get 1. So 1 and that function in terms of cos will be cos x plus 2t. Now, partial squared v partial x squared will be differentiate a cos function, you get a negative sine function. So we'll have a negative sign. Differentiating this part with respect to x, we get 1. 1 times the answer we got there, we have negative sign of x plus 2t. Call this one 2. So when I say 4 times partial squared v partial x squared, as I say, this implies that we'll have 4 into negative sine x plus 2t, which is minus 4 sine of x plus 2t. For this one, equation 3. I hope it should be obvious that 1 and 3 are the same. You see this equation, this expression and this one are the same. So therefore, I'll say clearly, question 1 equals to equation 3, which is minus 4 sine x plus 2t, i.e. partial squared v partial t squared equals to 4 partial squared v partial x squared. Then you rest your case. So that is how we prove that some functions satisfies all the equations. So thank you.